Hey everyone, in this video let's take a look at the quotient rule for derivatives. So much like the product rule, we need a special rule to work with functions that are written as the quotient of two other functions. We need to develop a special rule to find the derivative of these. To show you why we need a special rule, let's think about two just basic power functions. So let's say we have the function f of x, and let's say this one is equal to 3x cubed. And let's do a second function, g of x, and let's this one be x squared. So now let's go through, we'll find the derivative of these two functions right away. So f prime of x, using the power rule, the 3 comes down, so 3 times 3 we get 9x, and then reducing that exponent by 1, we get 9x squared. For g prime of x, again using the power rule, we end up with the derivative of 2x. So thinking about a quotient, this is going to be division. So let's write out f prime of x divided by g prime of x. And let's see what we get. So this is going to be the same as 9x squared divided by 2x. And that simplifies to 9 halves times x. Okay. So that's the quotient of two derivatives. Let's compare that to the derivative of the quotient. So we're going to do this in the reverse order. So let's define another function. Let's say capital F of x is equal to my lowercase f of x divided by g of x. So now in this case, we're going to find the quotient first and then take the derivative. So if I substitute in my two functions, we have 3x cubed divided by x squared, and simplifying that we end up with capital F of x. So our function here simplifies to just 3x. And now if I take the derivative of capital F of x, the derivative of 3x is just 3. So as we can see, the quotient of the derivatives is not the same as the derivative of the quotients. In other words, this fraction, f prime of x divided by g prime of x, this is not equal to capital F prime of x. So we can't just divide the derivatives. We need a special rule to work with functions that are written as the quotient of other functions. And let's develop that rule. All right. So remember the way that we define a derivative, and we're going to do this for capital F of x. So our derivative is the limit as h approaches 0, and then we have capital F of x plus h minus capital F of x, and this is all over h. And remember the way that we're defining capital F of x is this is the quotient of two functions. So we'll do lowercase f of x divided by g of x. So let's start plugging things in. So our limit is going to come down, comes down to every step. Here, capital F of x plus h, we're just going to replace the x's with x plus h. So we're going to have f of x plus h divided by g of x plus h. And then from that, we're going to subtract our original function, our original f, capital F of x. So that's just the fraction f of x over g of x. And this is still all over h. So we kind of have a messy fraction going on right now. And the first thing I'm going to do is I'm going to work with this a little bit to get it into a more manageable form before we start manipulating it so we can find our limit. So what that involves is my first step. In just the numerator, I'm going to get a common denominator and I'm going to subtract these two fractions. If I do that, so my limit keeps going. So if I do that, I'm going to end up with f of x plus h times g of x minus f of x times g of x plus h, and this will be over my common denominator, which is g of x plus h times g of x. And again, this is still all over h for now. All right, so I have a fraction in the numerator. It's a single fraction, and then we're dividing by h. I can rewrite that. So our limit as h goes to 0. So now I'm going to take that g of x plus h and that g of x, and I'm just going to move both of those into my denominator. So this is going to go from being a complex fraction to just a normal fraction. So we end up with this. All right, now the next step is we are going to add in some more terms so that we can work with our numerator a little bit. Eventually, our goal here, just like we did with the product rule, is I want to be able to rewrite some of this as the difference quotients for f and g, because we know that the limit of the difference quotient is the same as the derivative. So in this case, in order to be able to look at our difference quotients, we are going to subtract f of x times g of x. So we're going to subtract f of x times g of x. And since we're subtracting it, we're also going to add f of x times g of x. So adding it and subtracting it, that's like we're adding in 0. So we're not changing the value of this fraction at all. We're just putting in some more terms, and we're going to be able to factor with this. So we subtract it, we add it, and then we still have the minus f of x times g of x plus h. And this is all over our denominator that we have, h times g of x plus h and g of x. All right, the next step, after adding and subtracting those two terms, now we can do a little bit of factoring. So we can group these up. So let's look at these first two terms. These first two terms, they both have a g of x in them. So let's factor that out. So if we do that, we're going to be left with f of x plus h minus f of x, and this is being multiplied by g of x. Okay, so this is kind of where we're going. In the brackets here, what I'm left with, this is the beginning of the difference quotient for f. Let's do the same thing for our second two terms. So if we look at these two terms at the end of the numerator, those both have an f of x in them. Also, because I know I want this to end up being g of x plus h minus g of x, I'm actually going to factor out the negative f of x. And when I factor that out, what I'm going to be left with is the positive g of x plus h minus g of x, which is what we're looking for. So the next step is we need to complete the difference quotients for f and for g. So in order to do that, I'm going to take h from my denominator, and I'm going to move it into the denominator of a fraction within my numerator, and it's going to end up looking like this. So we still have our limit, and now I'm going to write this as I have my f of x plus h minus f of x, and now I'm going to write this over h. Well, this is still being multiplied by g of x, so I need that there. And then I also need to put h in the second term, so here I'll write it as f of x, and then this is being multiplied by g of x plus h minus g of x, and here I will put this over h. So because of our order of operations, we can rearrange this and we can do the multiplication division in a number of different orders. So what I'm saying is, instead of having the h down in the denominator of the fraction overall, I'm going to put that into the denominator of the two terms in the numerator. Okay, it's an equivalent fraction this way. In the denominator then, we are left with g of x plus h and g of x. All right, so we're almost there now. So we have our difference quotients set up. We have our difference quotients for f and g. So now let's separate this out and let's take the limit of the different pieces. So we will have the limit as h goes to 0 of our difference quotient for f. And this is being multiplied by the limit of g of x. Okay, and then subtracting. Now we're going to have the limit of f of x. And that limit is being multiplied by the limit of the difference quotient for g. So g of x plus h minus g of x. And this is over h. And then we'll use our quotient property for limits. And we'll take the limit as h goes to 0 of the denominator. So everything's separated out. We have the limit of each of these individual pieces, and we should be able to simplify and find the limit of all of this. So the first part, in the numerator of this fraction, the limit of the difference quotient for f. That is the same as the derivative of f. And that's being multiplied by the limit as h goes to 0 of g of x. Well, there's no h in here, so that's the same as just g of x. From that, we're going to subtract the limit of f of x. Okay, there's no h in that one either, so that's just the same as f of x. And that's being multiplied by the limit of the difference quotient for g of x, which is equivalent to the derivative of g of x. And in the denominator, here I can just plug in 0 for h. So the limit of g of x plus h is the same as g of x. And we're multiplying that by another g of x. So this is the same as g of x times itself. Well, I can write that as g of x squared. And there's our quotient rule. So we have the derivative of f times g minus f of x times the derivative of g of x, and that's all over g of x squared.